Morning, guys. Happy Sunday. Sorry I didn't get these done a little bit earlier, but I had some other things going on. So anyway, I'm gonna wrap up chapter 27 with three sections. Next three sections, three parts, and I will upload solutions to chapter 27 perhaps tomorrow or Monday, and we'll get you guys the next take-home quiz. Anyway, let's pick it up. So we're going to look first at what is called the internal resistance. So let's take a look at that first, and figure 27-4 is going to be important to look at while you listen to my lecture. So imagine we have a circuit which is made up of an ideal EMF, and then what we have here is we have an internal resistance I'm going to call lowercase r, and that's going to be connected to a resistance external to the source of potential difference, and we'll call that R. Sometimes this is, as I said before, this is called a load or a load resistance. So I'm going to call this point A, I'm going to call this point B, and we'll get back and see why I did that momentarily. But let's use Kirchhoff's voltage law, or the loop law, and let's go around this circuit. Let's go around this circuit in this direction. Okay. And so what we have here then, if we start on the low potential side of the EMF, then as charges move across to the positive side, we're going to have a voltage gain of E, script E, and remember, we're going to have an established current. There's going to be a current through this circuit. Be current I, and so the voltage drop across the resistor, which we'll just write as this at first. Okay. Actually, what we should have done is we should have looked at the voltage drop across the internal resistance. So I'm going to write this as V lowercase r minus the voltage drop across the external resistor or load resistor, V subcapital R. And that needs to be equal to 0, since we'll come right back to where we started. Now, using Ohm's law, we know that the voltage across the internal resistance is going to be the current times the resistance. We know that the voltage across the external resistance is going to be I times capital R. It's going to be equal to 0. And we'll recognize that R, lowercase r, and capital case R are actually in series. Now, we're gonna formalize this later, but for electronic, I'll state it here, for electronic devices connected in series, the current is identical in each device. So in this particular case, we have we have two resistances that are in series. And we'll, again, formalize what it means to be in series, but that's connecting those devices head to toe without anything in between them, okay? No intervening devices between them that are looping off. And again, as I said, we'll formalize this as we have this discussion. So then this expression can be simplified if we factor out the current, since the current's the same in both devices, and we can actually solve for the current, which now is going to be equal to the EMF divided by the sum of the resistances. Okay, now that's important, and I want you to recognize a couple of things, right? So the internal resistance is important for controlling the current as much as the load resistance is. So the whole idea here is that in sources of potential difference, you want to try to reduce the internal resistance to as small a value as possible. So if we go back now, and if we look at the potential difference between A and B, then that potential difference is going to be equal to the ideal electromotive force script E minus the voltage drop across the internal resistance, which is going to be equal to script E minus I times R. And we know what I is, so that's going to be equal to a script E minus script E over R, lowercase r plus capital R, times lowercase r. So that now, right, this is going to be positive for sure, right? So this will be always greater than 0, which means that V, right, is going to be less than or equal to the EMF. So, you know, if the internal resistance were equal to 0 ohms, then V is going to be equal to script E, the EMF. If R is greater than 0 ohms, then V will be less than script E. So the electromotive force then, is going to be the maximum voltage that can be delivered. Maximum voltage that can be delivered. And sometimes we call V, this is going to be the terminal voltage. Not terminal in the sense of end, terminal in the sense that it's the voltage across the terminals of the battery, A and B. Okay, so that would be the terminal voltage. Okay, awesome. So now let's take a look at a next circuit, and from here on out, unless specified, right, we're going to assume ideal EMFs, right? That is that the internal resistance is equal to 0 ohms. Okay? So if we look at, and I'm going to come down to the next page here, right? So if we look at the following circuit, so here's an EMF. Here is one resistor, two resistors, and three resistors. Here's the EMF. We'll call this R1. Call this R2. We'll call that R3. It's the positive side of the seat of EMF. Wires are going to be considered ideal. So wires are ideal. And that means that there's no resistance. No resistance. And the EMF is ideal. And we just stated that above, right? That means the internal resistance is equal to 0 ohms. And so what do we want to know? Well, in circuits, there's only two real things to know, right? It's we want to know about currents, and we want to know about voltages across devices. Okay, currents and voltages across devices. So let's move around this. We'll move around this circuit in this particular direction. Okay, and we'll start here. Okay, and just move around that circuit, and we'll use Kirchhoff's voltage or loop law. We want to recognize a couple of things, right? So the apparently sharp edges here of the circuit, right? So here, and here, right? I can soften the edges of this circuit. Right? I can soften the edges, and I can actually write that circuit as something that looks like this. And actually I can soften this a little bit more. All right, so there we go. Again, here's our EMF, R1, R2, and R3. And I want you to recognize here that R1, R2, and R3, R1, R2, and R3 are in series. So again, we can formalize this, right? So that when we have devices that are connected in a head-to-toe fashion, so there's device 1, device 2, device 3, and they're connected in a head-to-toe fashion, we say that these devices are in series. And there must not be any intervening electronic devices. So, for instance, if we were to hang a device, say here, device 4, then 2 and 3 would not be in series, but device 1 and 2 would be. Right, device 1 and 2 would be in series. Okay, so this connectivity head to toe between devices with no intervening devices means that those devices are connected in series. Okay, so for devices connected in series, so going back to this picture. So devices that are connected in series, device 1, 2, and 3, then I'm going to choose pink here, then the current through current through each device is identical. So the current through each device is identical. And if you think about it, that's almost common sense. But let's just think about that. That means that current moving through these devices can't bunch up, right? So current can't like bunch up here and then be less in device 2 than in device 1. And likewise, current can't spread out. And so current can't bunch up or spread out, and so it's like water going through a hose. The current going through these devices then is going to be maintained and be identical throughout each device. Okay, so let's go back up then and look at our circuit here and use Kirchhoff's voltage law. Again, starting on, as I said, starting on the low potential side of the EMF. Then we look at the sum of voltage gains and voltage drops. So that would be script E. Charges will get a voltage gain in going from here to here. And then there's going to be a voltage drop across R1, a voltage drop across R2, a voltage drop across R3, and we come right back to the zero potential side of the EMF, and so those sum of voltage gains and voltage drops must be 0. So again, we can use Ohm's law, and so the voltage drop across, right, the voltage drop across R1, the voltage drop across R2, the voltage drop across R3, right, can be calculated because we know that the current going through each of these devices is identical. The current going through each of those devices is identical. And so then this is going to be the current times R1 minus the current times R2 minus the current times R3 must be equal to 0. We can factor out the current since it's the same in each device. And so we can actually write the sum of R1, R2, and R3, right, as what we call an equivalent resistance. All right, just EQ from here on out, so E minus I times R EQ is equal to 0. And it means that actually what we could do is replace those 3 resistors with its equivalent, that is R equivalent. And so the same current, right? The current would be identical as in the original circuit, so it's still going to be I, except that now we can replace the 3 resistors with an equivalent resistors. Now, you might say, that seems silly, right? Then why did we use 3 resistors to begin with? And that's not going to be part of this discussion of where in electronics we might want to make these kinds of transformations. But the bottom line, right, for us is that for resistors in series, then we can get an equivalent resistance merely by the sum of the resistors in series. And it doesn't need to be 3, it could be 300. And so we write that most generically as I is equal to, you know what, I shouldn't use I, we'll say I is for current. So let's just say this is going to be K. Let's use K. Actually, let's use N. I know I'm being crazy here, but let's use n equals 1. Well, actually, let's use k. Here we go. So use k is equal to 1 up to the number of resistors r sub k, okay, using summation notation. All right, very good. So that's for resistors in series. We've got some practice with Kirchhoff's voltage law. We now understand that for devices in series, the current is identical through all those devices. And so we'll end here, and we'll pick it up in talking about circuits where devices are in a parallel configuration. All right, very good, folks. Stay tuned.